Chapter 3 Matter, Energy, and the Universe. Section 3.3 Energy. So scientists define energy as the capacity for doing work. At the beginning of the 20th century, Einstein suggested that energy and matter are related to each other at the atomic level. He suggested that atoms have within them large amounts of energy. Scientists were able to extract the atomic energy found in matter beginning in the 1940s, using a process called nuclear fission. Here's the results of nuclear fission: an atomic bomb. In 1998, energy was successfully transferred into matter, as Einstein predicted. Energy and matter have associations to each other at much larger scales of nature. For example, plants convert solar radiation into organic matter through photosynthesis. Plants absorb electromagnetic radiation in the form of light, and in chloroplasts, they convert this energy with the addition of water and carbon dioxide into organic matter, or organic energy that can be used by the plant later on. Let's now look at the variety of forms of energy. So we're going to look at the various types as defined by physicists and chemists. We can suggest that two main forms of energy are kinetic energy and potential energy. Kinetic energy is the energy due to motion. It could be the energy contained within an atom. It could be atomic energy due to the vibration of an atom. Or kinetic energy could be a boulder rolling down a hill. Potential energy is the energy stored by an object that can be transformed into another form of energy. In this slide, we see a wave approaching my daughter, and that would be kinetic energy. That wave, when it hit her, knocked her over. Here's a type of potential energy that many of us use in our cars: gasoline. Some other forms of energy include heat, electricity, sound, energy of chemical reactions, energy of magnetic attraction, energy of atomic reactions, and the energy of light. In science, it's useful to be able to measure energy. We measure and quantify energy using standard set of units. Two systems of units of measurement are commonly used: the metric system and the British system. Measurement units in both of these systems are derived from a specific technical definition. This definition suggests the following equation: work is equal to force times distance. A Newton is equal to the force needed to accelerate or move a mass weighing 1 kilogram 1 meter in 1 second in a vacuum with no friction. This is a standard measurement of energy that is then used to derive other units of energy. The work or energy required to move an object with the force of 1 Newton over a distance of 1 meter is called a joule. Let's define some other important measurement units that we'll be using in this course. A calorie equals the amount of heat required to raise 1 gram of pure water from 14.5 to 15.5 degrees Celsius at standard atmospheric pressure. 1 calorie is equal to 4.1855 joules. A form or unit of energy not used that often anymore is a BTU, You might still have something in your home that describes its energy use in BTUs. BTU stands for British Thermal Unit, and it is the amount of energy required to raise the temperature of 1 pound of water 1 degree Fahrenheit. I'm going to be showing you all kinds of graphs and maps that display the unit known as a watt. And watts are a measurement unit used to figure out the intensity of radiation over a unit area. The unit area that is most commonly used is a square meter. So it's watts per square meter. 1 watt is equal to 1 joule of work per second. So joule and a watt are equivalent. If you have to pay energy bills, then you're probably familiar with a kilowatt. And a kilowatt is just 1,000 watts. Let's now examine energy, temperature, and heat. One definition of heat energy is that it's the kinetic energy of atoms and molecules. Kinetic energy is also related to the concept of temperature. Temperature can be defined as the measure of the average speed of atoms and molecules. If a substance's temperature changes, if it increases, the average speed of the atoms and molecules also increases. If you cool a mass to absolute zero, the average speed of the atoms and molecules becomes zero. So, at a temperature of minus 273.15 or absolute zero, all atomic motion stops. Now, heat and temperature are not the same thing. Heat can be defined as the energy in process of being transferred from one object to another. Heat occurs if a temperature difference exists between the objects. So, for example, if we have two objects of the same temperature and put them beside each other, there is no heat transfer. However, if I put a hot piece of metal beside an ice cube, there is heat transfer, and the ice cube will melt, and the water will be produced and increase in temperature, and that piece of metal will cool down. In the atmosphere, heat is transferred mainly by 3 processes. These 3 processes are conduction, convection, and radiation. Conduction is the molecule-to-molecule transfer of heat energy, so the molecules have to come in contact with each other. Convection is a mass of molecules with stored heat energy moving vertically into the atmosphere, or if that movement is side to side, it's called advection. Radiation is the transfer of energy from a mass by the emission of electromagnetic rays. Here are some other important heat definitions. Heat capacity is the ratio of the amount of heat energy absorbed by a substance to its corresponding temperature rise. We can standardize heat capacity by saying that we're only going to deal with 1 gram and a temperature rise of 1 degree Celsius. This new thing is a definition called specific heat. So specific heat is the heat capacity of a unit mass of substance or heat needed to raise the temperature of 1 gram of this substance 1 degree Celsius. The various substances that exist on the Earth have different specific heats. In a relative sense, the specific heat of gold is much lower than the same amount of water. Sensible heat is the heat that can be measured by a thermometer. And we have several different measurement scales that we can use to measure sensible heat. There's Fahrenheit, Celsius, and Kelvin. Kelvin is what is used in science. Latent heat is the energy required to change a substance to a higher state of matter. Latent heat is released when the change of state is reversed. So here we have the latent heat of water. We're dealing with 1 gram of water. And in order to move water from solid to liquid, we would have to add 80 calories of heat energy to that 1 gram of mass. To change that 1 gram of mass from liquid to vapor would require another 600 calories. Where is this energy going? It's going into the atoms and molecules and causing them to vibrate quicker. When we reverse the process, the energy is released from the atomic mass of this water. So when we go from vapor to liquid, 600 calories is released from the molecules of water into the environment around them in the form of heat energy. If we go from liquid to solid with 1 gram of water, we're going to release another 80 calories of heat energy into the environment. In our atmosphere, this latent heat process and its association with water moves a lot of energy about the Earth. At the tropics and subtropics, large amounts of water are evaporated from the oceans and land surfaces, and this requires heat energy from the sun. This vapor then is transported by circulation to the middle and high latitudes, where it condenses out or forms snow, and this releases heat energy that originally came from the subtropics and tropics to the middle and high latitudes.